Good afternoon, ladies and gentlemen, and welcome to our webinar on MotorSolve DCM. MotorSolve DCM is a simulation software for the design of brushed or commutated DC machines. MotorSolve DCM is an electromagnetic simulation. It's based on 2D finite element method technology. The available experiments are provided with either a partial reliance on finite elements or a full reliance on finite elements. MotorSolve DCM simulates the full experimental process for physical prototypes. In essence, virtually prototyping. MotorSolve DCM is a design software. It allows you to assemble the components by defining each of them individually with respect to geometry, and then to assign the corresponding materials that you desire. This is followed by the definition of the excitation and the initial conditions for a given experiment. An experiment is run, and then the user reviews the machine's performance. When you open a new session in MotorSolve DCM, you have three interface components. You have a top left tree area, which controls the experimental process. You have a bottom left interface area, which allows you to declare text fields and configure the machine according to your needs. And then on the right, you have a corresponding change to the geometry, which gives you a visual impact or feedback on what you've chosen to do. The basic design parameters under the general settings requires that you enter a supply voltage and a rated speed. This is standard sort of template data. This is followed by an overall geometry or envelope of the machine, which requires you to enter an outer diameter and a stack length, and then also an air gap thickness. Note also that you are required to enter kind of a configuration choice for the stator type and the armature type. MotorSolve DCM comes with a wide variety of template-based choices that you have for permanent magnet assemblies, as well as a wound field configuration. And then new technology has allowed us to offer a DXF import, and this will allow you to enter any sort of innovative new constructs that you might have for your stator in the form of the general configuration. And then with a simple choice of the number of poles, the interface will respond accordingly. Additionally, for the armature, we have a wide variety of template-based inputs which allow you to enter the armature cross-section, as well as an option for importing any sort of innovative concepts that you might have with respect to a DXF import. Once you've configured the machine in a general perspective, you then navigate through the tree to specify more information according to the specifics for that configuration. So rather than go through the interface with our default machine, I've chosen a specific machine here, and we're going to go through the interface and look at the specific parameters associated with this example. So you can see here that I've created a general configuration for both the stator and the armature. And now if we go into the extended configuration parameters for the stator, we can see here that there are specific parameters associated with the machine. And we can see that with changes to the parameter, there is a corresponding change in the geometry to the right. Note that MotorSolve has a inherent ability for geometry protection, I'll call it, which allows you to define which of the associated parameters for this configuration you would like to not be automatically changed by changes in other parameters. So you can see here that we are going to create a scenario where we're not going to allow changes to the angle or the thickness or the width of the magnets as a function of the other parameter definitions. And we can still make changes to these. As you can see, these are referenced by the color changes on the left. But this allows you to very cleanly go in and define the geometry for your stator. Likewise, if we go into the armature area, we can see here that there are a range of parameters which need to be input. Again, you can see that there is a dimensional line and a label for each of the parameters as you step through them. And you can go in and clearly define and reference the specifics for the definition associated with your configuration. Another part of the armature definition is the winding. So in the armature windings area, you see here that you have new available parameters for describing things like the slot liner, coil separator, the notion of the actual conductor itself, whether or not it's diameter or standard gauge wire, whether or not there are parallel strands in hand which are wound with the winding, whether or not it's a lap or a wave winding, whether or not it's a progressive or regressive winding, the notion of the number of coil spans, number of turns, all these things are defined in the winding area. And then perhaps one of the most interesting parts of this interface, you can use this slider to review a range of possible armature positions and the outcome that that would have on the winding. Additionally, you can also do that with the brush shift and see how the conductors get energized and respond as a function of these differing angles. An additional winding interface area is for the end winding and the definition of the end winding. And then the final area for the armature is the definition of the actual commutation and the notion of whether it's got commutation and brushes and what those definitions are with respect to these given parameters. Once your geometry is completely defined, you then need to assign materials to the various components. One of the strengths of the MotorSolve product is its ease of use with regards to assigning and creating materials. There is an extensive library available with the product. And you can see just a small glimpse of the variety of materials that come with the product. You can add materials very easily and use your own, and this is actually encouraged so that your experimental process and conditions for the experiment are equivalent to your physical components that you might experiment with. But once you go into this material area, a simple pull down and slide and assign allows you to clearly define the material for the components. You'll also note that the various portions of the components are separated, also for ease of use, and our database allows for this separation so that things can be cleanly or more cleanly identified and assigned. And once you have the materials assigned for your device, it's then ready to review and go into the experimental area. We call this experimental area the results area. But you can see here that there's a wide variety of experiments to run. We have cogging torque, we have a back EMF, we have back EMF constant, we have a torque constant, torque speed versus torque, air gap flux, motion analysis, instantaneous fields, and then probes, a line probe and an arc probe. For each of the selections here, you will see that there's a corresponding input area, which requires and allows you to describe the actual experiment. And we're going to step through each experiment. So let's explore the cogging torque experiment. Here we can see the result of the cogging torque, and you can see that it's in electrical degrees or mechanical degrees. But you can see clearly defined cogging torque for this machine. One of the clever features of the MotorSolve interface is that if you are to click on this vertical bar, you can see here the corresponding value for the X and Y axes as you ride along the curve. Another feature which is very handy is that you can actually view the data in any of these graphs. And this is just a table of values for the curve. You can export it to either a CSV file or an Excel file. And one of the additional features, which is very handy, is that you can actually add it to a report. And this report is a live laboratory notebook type of area, which allows you to record both the inputs and the responses of your machine. It's tabulated in the report area. You have a notion of a header that you can add. You can add text as you desire. With the selection of the add button, this particular part of the experiment or part of the modeling process is added to the report. You can see here under the report tab that you have a page in the report, and when you're done with the modeling process, you can actually export the report to either a PDF file or to an HTML file as you desire. Now let's explore the back EMF experiment. What it provides you with is a specific voltage associated with the speed of the machine, and you see here that we have a tabulated value associated with that. Additionally, if you want to review the back EMF as a function of parameters, you can choose to do the back EMF as a function of either speed or of shift angle. For the sake of discussion, we're going to run an experiment which shows the back EMF as a function of the shift angle from minus 45 to plus 45 degrees in 15-degree increments. You can see here the corresponding result. And note in the interface area that we have clever ways of entering particular parameters. You can choose to enter into a list. This could be uniform or not. It's just a single list of values separated by commas. Or you can enter a range of values, such that I have here. And this allows for flexibility as you go through and look at the various parameters and experimental conditions that you want to review. Now let's explore the back EMF constant experiment. Selection of this experiment also allows you to do it as a function of brush angles should you choose. In this case here I just use the default value. You can see here that we have a little over 8 millivolts per RPM. Now let's explore the torque constant experiment. Again, we could give a range of values for the shift angle, should we choose. In this case here, we're just going to do the default of 0. You can see here that we generate roughly 80 millinewton meters per amp. Now let's explore the speed versus torque experiment. For the speed versus torque curve, we have 3 parameters which we can control in the experiment. One of those is the percent of rated voltage that we use. Another of those is the brush shift angle. And finally, the third of these is the armature speed. And you can see here that in this experiment we're going to leave the rated voltage at 100%. The shift angle is going to remain at 0. But we're going to do 3 speeds for our speed versus torque. And the result is shown here, where we generate on the order of 1.5 Newton meters at a little over 35 RPM. We generate a little over 2.5 Newton meters, or right around 2.5 Newton meters at 2,500 RPM. And if we go out to 1,500 RPM, we have about 3.4 Newton meters. One of the advantages of the finite element method is that you have the local field values everywhere in the solution space. In this case, everywhere in your machine. And so the presentation of the air gap flux is a natural fallout of that solution. Let's look at some air gap flux solutions. And you can see here that for armature position of 0, we have a flux response in the air gap. And we can tell the precise nature of the air gap associated with where the magnet starts and stops here at the extremes. And then if we vary the armature position, we can see the change in the flux. So let's choose another angle. Here we've set the armature position to 5, so we're going to have a rotation of roughly 5 degrees. And you can see that the pole location has changed relative to the stator. And likewise, if we go to the 10-degree position, again we can see the change associated with the pole. And one final angle. Let's look at 15 degrees. Again, we can see the change associated with the change of position of the armature here at 15 degrees. So I mentioned in the initial part of our discussion here that MotorSolve uses either partial reliance on finite elements or a full reliance. And what I want to underscore here is that these performance chart experiments on the top of your listing here, these are all experiments which utilize finite elements, but they use clever assessments of the experiment to not have to rely and do a full transient or a full simulation of finite elements, and so computation time is minimized in that regard. If, however, we choose to do a motion analysis, This is a full-time transient, and we're going to do a few of those to showcase the performance of MotorSolve. Note that we control the experiment with the inputs here with voltage and speed, and then we're going to review the experiment and the behavior of the machine, and we can look at various constructs. So the first thing to note is that you can look at either a waveform or the time average or a split up of harmonic content of the response that you've chosen. Additionally, you have a series of global parameters that you can review. In this case here, we're going to look at the voltage. So here we have a voltage on the first 4 phases of the machine. Likewise, if we toggle this to the current, we can review the 4 currents associated with those phases. And perhaps more interesting is to review the torque associated with the machine. And you can see here at rated speed, rated voltage, we have roughly 2.5 Newton meters as the output torque for the machine. If we switch this to the time average, we quickly see that we can tabulate additional constructs. And so let's go ahead and do that. And you can see here that we have a table, a tabular view. We have 2.55 Newton meters as the waveform average. You can see here that our efficiency is just about 47%. And this gives you a clear indication of the performance of your machine. You can see here that we have an input power of about 1.4 kilowatts and about 670 watts output. Now if we alter the conditions for the experiment slightly and we look at the time transient associated with what happens if we review this with a brush shift angle of 5 degrees. Again, we can look at the various experimental results. The voltage looks a little bit messier. The current looks approximately the same. And the torque is still roughly the same. So a brush shift of 5 degrees doesn't look like it is a dramatic impact to the response of the machine. Let's look at one additional experiment here for the motion analysis. And in this case here, we're going to shift and look at 10 degrees for the brush shift angle. Again, we can look at the voltage. We can look at the current. And the torque. And I believe that the time average is roughly the same, but you can see actually that it's lowered by some. We had 2.55, we're now below 2.52. And we've lost a little over 1%. It's probably not significant. At this point, we're going to review another motion analysis. The operating conditions for this particular experiment are going to be at 4,000 RPM and 80% of rated voltage. Here you can see the voltage waveform. Here we have the corresponding current waveform. And finally, the torque output. With the solution of the finite elements, let's look at the instantaneous fields and review the local distribution of the flux densities. Here you can see the flux density throughout the entire machine. This will be instructive when trying to assess thicknesses of permanent magnet, thicknesses of the surrounding core iron for the stator. It'll also be demonstrative and can help with the choice of the definition of the teeth for the armature, so that you can review whether or not and if you are saturating, and whether that's a derogatory thing or not, depending on the design criteria. Note also that there's a feature in MotorSolve which allows you to zoom into a particular area of interest, and here we can see very clearly the distribution of the flux in the core of the stator. Now we'll explore the local flux distribution using the field arc probe. You can see here the local distribution along the arc, which goes from 0 to 360 degrees around the machine. And we have a low of 0.05 Tesla to a high of 0.5 Tesla. You can see the periodicity as we go around through the magnet area. Should you choose to, you can change the value of the arc, or the radius for the arc. So for instance, if we'd like to, we can change the value of the radius and review the fields. Here we can see the flux response in the actual surrounding core for the stator. So you can see excursions here well above 2 Tesla for this machine and the operating condition chosen. At this time, I would like to showcase the use of the software for multiple designs in the same model. Note here that I have created 3 designs in my tree. The 3 designs are identical except for the extent of the arc associated with the permanent magnets in the stator. And in design 1, we have an arc defined in the stator of 125 degrees extent. In design 2, we have an arc assigned to be 135 degrees, which was the original value. And then in design 3, we have an angle of 145 degrees for the extent of the magnet. And what we're going to do is we're going to look at a few key parameters associated with the review of your machine. So in this case here, we're going to solve all 3 physics problems associated with your prototype or your designs within the model. You can see here that I've checked all 3 designs. And when we run the cogging torque as a function of my 3 experiments, you can see here the change in the cogging torque as a function of those small modifications to the design. And you can see here, as you propagate through the presentation of the lines, that you can find exactly which line is which. You can see as you review things that the lines are designated and the y-axis or y-intercept for each of the curves is clearly presented to you. You can see here in the difference of the design as a function of the angle of the magnet, the extent of the magnet, and in all likelihood the use of the design 1, which was the smallest of the angles. You can see that it clearly provides you with the most cogging torque, and it's likely not going to be a desired choice option if cogging torque is to be minimized in your machine. And one final construct that I'd like to showcase for you with regards to the multi-design. Again, we have the same three designs where the permanent magnet angle has been varied, and this time we're going to just review the change in the back EMF as a function of those designs. And as you can see here, the solution for the back EMF is in tabular form, and we can clearly see that with the least amount of magnet we have the least amount of back EMF. It's rather intuitive, but it's nice to get confirmation of this construct or the solution response. With the most amount of magnet we have a larger back EMF. So by assessing this sort of thing, we can get a good feel for the response of the machine as a function of the volume and therefore the weight of things. So you can see and envision that the use of the tool would allow you to optimize weight and cost and optimize the overall performance of your machine. It's my hope that these examples and this demonstration in the webinar has been instructive. At this time, we're going to open up the webinar for questions. Thank you for your time. Have a good day.